Hey, we've talked about increasing and decreasing. We've talked about finding local maxes and mins. Our work is done, right? No, there's more we can do. We will be able to find the intervals where a function is concave up or concave down. Now, these are new terms for us when we get to calculus, so let's take a look. We got graphs there. Concave up there on the left. Think the graph is curving up. If the graph is curving up, it's concave up. And concave down, well, it's like it's curving or curling, maybe is another word, curving down. Okay. Well, how are we going to be able to identify when a function is concave up or concave down? It's actually all about the second derivative here. You're concave up if your second derivative is positive, and you're concave down if your second derivative is negative. Now, this is not nearly as obvious or as intuitive as the first derivative with increasing and decreasing. So let me just take a quick moment to explain why this would be true. So the question I've got there, why does this shape give either f double prime x greater than 0 and f double prime x less than 0 for their respective concave up, concave down shapes? So here's my explanation. If this is the original function, right, and it's got this shape to it, let's think about the first derivative. Okay, so if it has this shape, well, then at some point it was at a minimum, right? And at that minimum, the tangent line is horizontal. That's the 0. I tried to draw it directly underneath. Okay. So what's happening on either side? Tangent lines are negative. So we've got negative values. Then it hits the 0, and then tangent lines are positive. So it's got the positive values. Negative, 0, positive. Now think, okay, if this is more or less, I drew it as a straight line. It might not necessarily be a straight line, but it's good enough. If this is a good idea of the first derivative, then what's happening with the second derivative? Why would it be positive? Well, you think any point on this first derivative, if you were to draw the tangent line of that, right, the derivative of the derivative, what's any tangent line doing here? Well, it's going up. So any tangent line on the first derivative has a positive slope. So that means the derivative of the derivative is positive. The second derivative is positive. Okay. Similarly, back over this way, at the very top on the concave down, right, that derivative is 0 right here. And then if you look on either side, okay, these derivatives are all positive. These are negative. So we got the positive, negative, positive, 0, negative. This would be a good idea of the first derivative graph based on that original. You think, okay, if that's the first derivative, then what's the derivative of that? Well, any point has a negative slope for its tangent line. So that second derivative is negative. Okay, in the end, you don't need to know all this explanation, but it gives a greater depth, and it's a good thing. It's always a good thing to know why you do what you do, right? Okay. So here's our concavity test. And I'm just going to show you all these tests. Oh my goodness. They're similar though, right? Similar enough to be confusing. All right, so the concavity test, I'll just show you the whole thing. It's actually exactly the same as the increasing decreasing test, but we're using the second derivative now instead of the first derivative. So let's read through it. Step number 1, find the x values where the second derivative equals 0 or the second derivative does not exist. That's exactly what the critical numbers are, but with the first derivative, right? So essentially, we're finding the second derivative critical numbers. where they equal 0, where it does not exist. Okay. Step number 2 is the same. We're going to think of a domain line. We're going to mark these x values on that. And step number 3 is the same. We're going to test each interval, but we're going to test it in the second derivative because we're looking at concavity. And so when we find those positives or negatives, then we know, oh, that's concave up for positive, concave down for negative. All right. And then I've got my note here. It's the same as the increasing, decreasing test, but with the second derivative instead of the first derivative. Before we do an example, we also want to define an inflection point. An inflection point is the equivalent of the local max or the local min. So for concavity, where it changes concavity, we call it an inflection point. Let me give you just a quick little sketch over here on the side, kind of make sense of the name. So let's say a function was concave up, and then it switched to concave, oh, said that backwards. Let's say it's concave down, and then it switched to concave up. So it did this sort of a shape, right? We're curving down, and then at some point it transitioned and became curving upwards. So maybe that point right there is where the switch happened. It was curving down, then it started curving back the other way up. So that would be an inflection point. And I think the name is fitting. It's like, almost like, flips inside out. It inflects. I think of like a piece of rubber, like a rubber cap or something, and it's like being popped inside out. Okay. So here's what we're going to do. We're going to find intervals where the function f of x is concave up and concave down. Once we know where it's concave up and concave down, then we're going to locate inflection points. And those inflection points, once we have the concavity intervals, it's going to be just a matter of looking at our domain line and the way the positives and negatives work. Okay. Our function here is a good one. F of x equals x to the fourth e to the negative x. All right. Well, let's go for it. Since we're looking for concavity, we need to find the second derivative, right? So we got to find the first derivative, then from there we find the second derivative, then we find those x values where it's equal to 0 or does not exist. Okay, it's not a short problem. And we want to be really careful with taking our derivatives, especially now that we have to take two derivatives, doubles the chances for an error. Okay, so looking at it at first, we know we've got a product rule. And there's even a chain rule happening there with the negative x. Okay, so here's our first derivative. Product rule says 4x to the third times e to the negative x plus x to the fourth, and then our chain rule times e to the negative x times negative 1. And let's just clean that up. Move that negative out right there. Whenever you need to take a second derivative, you really want to simplify your first derivative as much as you can. And here there's not much, but in other cases there might be. Okay. All right. Now for the second derivative. We got to make sure we nail this, okay? Look right here. This term is a product rule. This is a product rule. Two product rules. Let's go for it. Here it is. Slide over a little bit, fit the whole thing in there. Here's our first product rule. 12x squared times e to the negative x plus 4x to the third times e to the negative x times negative 1. Okay, we'll simplify that in a moment. Minus, this is big. This has not come up in a lecture before. Subtracting a product rule. If you are subtracting with a product rule, you have to make sure that negative goes to both parts. So put a negative sign and then throw a parentheses there and then just do your product rule. So I'm going to put minus parentheses and then do my product rule. 4x to the third times e to the negative x plus x to the fourth times e to the negative x times negative 1. That's the same derivative as the first one, but I'm subtracting the whole thing. Again, even something as simple as missing those parentheses and missing that this becomes negative, oh, that will just throw off everything when you're trying to solve. Be very careful. Go through this slow. It's not a rush. Now, over time, you want to be able to get faster just because your derivative skills are better, not because you're rushing. All right, let's clean that up a little bit. So, okay, not much there. This is minus. That's subtracted. This is actually positive because we have that other negative 1. So the negative and the negative 1 plus x to the fourth e to the negative x. And you notice, oh, wow, these terms in the middle are actually the very same term. So we can go one step further. And here it is, f double prime x, 12x squared e to the negative x minus 8x to the third e to the negative x plus x to the fourth e to the negative x. And it took us 1, 2, 3, 4, 5 steps just to get that second derivative. One thing I've noticed in students' work, some students really take a lot of steps to do their derivatives, and I think that's a great idea when we're in chapter 3 and we're learning derivatives and you're really breaking it down into every little step. But as we get into applications, those steps need to become fewer and fewer, and they need to just become the essential steps for the derivative. Because you don't want to take 2 pages of work just to get a second derivative. That's so much time. You just cannot spend that much time getting a second derivative like this. Okay. And homework, fine. On tests, that's just too much time. All right, we've got our second derivative. What do we do now? We're going to set it equal to 0, right? Start to find, they're not criticals, but the second derivative criticals. All right. So there, setting it equal to 0. All right, think factor. Factor. What do these have in common? Well, they all have e to the negative x. They all have x squared. So let's take out x squared e to the negative x. And already that's looking a lot better. X squared e to the negative x, and it left behind 12 minus 8x plus x squared. Now it turns out what's inside here will factor further, but we need to rearrange things. Put that in the proper order, and then it will factor even further. Let's just leave it right there. X minus 6, x minus 2. And we're looking really good. What are the x values that come out of this? And I'll just show you these first, right? So this one set equal to 0, x equals 0. This one, x equals 6, x equals 2. Very nice. There is another factor in this whole thing, e to the negative x. Well, let's see what happens with that. If we set this factor equal to 0, it turns out there's no solution. E to the negative x equals 0. If I just get rid of that not equals for a moment. If we think, hey, is this possible? Could that equal 0? We'll try it, right? Take the natural log of both sides. Oh, but wait, the natural log of 0 does not exist. Or maybe you could think about it another way, like what x value would you plug in to make this 0? Well, even if you plugged in 0, that'd be 1. and any other number would be positive, actually. So this just does not produce another solution. These are the critical numbers, 0, 6, 2. Okay, this can stump people, so yeah, it's good we have an example with that. Now, of course, we need to consider, hey, any x values where that second derivative does not exist, right? Here was our second derivative. L, in this case, no, it's still none. I think that's been the